Okay, so now let's have a look at the LTL properties. We've seen how to build a reachability graph, how we can use it for basic system analysis, and we'll see LTL logics now in order to express more elaborate properties. LTL is a linear time, as a linear time semantics, and therefore it considers paths of executions. So as you can see here, you have 3 paths of executions, 1, 2, and 3. These 3 paths of executions would say in the first one, so the one that is red, I start in state S0, and then I go to state S1, and then S3, and then S0 again, and S1, and S3 again. And as you can see, it could be something like a loop, but it's a path that is described, and you go and see what happens along the path. In the red path, you will start with S0, and then S2, and then S5, and S0, and so on. So linear time logic will consider paths of executions and express properties on these paths. As concerns the syntax of this logic, we'll start with a set of atomic propositions, AP, and if we have a formula, A in AP, that is an atomic proposition, well, it's a LTL formula. And if you have 2 LTL formulas, phi1 and phi2, they can be combined, or you can construct more elaborate LTL formula from them. So it can be negated with negation of phi1 here. Or you can do a conjunction of the 2 formula. So you can have phi1 and phi2, or you can have other operators, x phi2 and phi1 until phi2, u phi2, where x stands for next and u for until. And so they express what happens next, or what happens. A formula should be satisfied until another one should be satisfied, is satisfied. You have also in the literature a lot of, some shortcuts that are generally used. So in these shortcuts you have F. F phi says something is true until you have phi, and G phi is the negation of F not phi. So F stands for future and G for globally. So basically F says something will be true in the future, while G says that something is globally true. We'll see how it can be depicted next. So with each LTL formula can be associated language, and you can see that a sequence of execution sigma is in the language of a formula phi. If and only if you have the following things for the basic construct. So sequence sigma is in the language of formula A, where A is an atomic proposition, only if A is satisfied in the first element of this sequence. So that is written as A in sigma of 0. So the first element of the sequence satisfies the atomic proposition A. Now, for the negation of a formula phi, we have to verify that sigma is not in the language of the formula phi. For the phi1 and phi2, it boils down to saying that the sequence is both in the language of phi1 and the language of phi2, so in the intersection of the 2 languages. As concerns the next operator, you can see that here you have sigma of 1. So it's not the first state, it's not the first state S0, it's the next state. and X means next operator. So I have in my sequence a first state, and the second state I check whether it satisfies phi. And finally the last one, so phi 1 until phi 2, consists in finding an element I, so an index in the sequence such that the sequence at this index satisfies phi 2, and for all indices before I, so all those that were before I, the element in the sequence satisfies phi 1. Now let's depict it with some sequences. That is maybe easier to understand. So as concerns atomic proposition A, you just have to see that the first element in the sequence here satisfies A. So you can see in these pictures the formula that have colors, so red or blue, and on the path here, the red dots or blue dots just mean that this state satisfies formula, the red or the blue formula. Right. The second sequence, we wanted to satisfy x phi. So in the next element, so I don't take the first one, I take the next one, and it should satisfy phi. Phi 1 for phi 1 until phi 2, we have two examples. So the first one, you can see phi 1 is satisfied, it's the red formula, it's satisfied all the way until I find an index where phi 2 is satisfied. Well, afterwards anything can happen, we don't care. But phi 1 must be satisfied all the way until we find phi 2. But the possibility is to have also phi 2 immediately satisfied. So phi 2 is satisfied at index 0. Formula f phi, so in the future I have phi that is satisfied, consists in saying, well, true is true all the way until phi is satisfied. So sometime in the future I will have a state that satisfies phi. Finally, the last formula is globally phi, which means all states satisfy formula phi. And as you can see, all states in the sequence are labeled with the formula phi. So they are red, being pictured in red. Okay. As concerns symmetric nets, so let's take again the basic example. We'll have the atomic propositions that are P of C and T of C. So P of C means that place P is colored with contains token C, and T of C will mean that I can find transition T with color C. So let's see two examples of formula. The first one here, which says globally not BZ of C1 and BZ of C2. That means that if place BZ contains C1 and contains C2, well, that can't be the case. So in all states, I must not have place BZ contains C1 and place BZ contains C2. So they do not appear together in place BZ. And that is something we want in this example because we just have one resource that we share, and only one of the processes, C1 and C2, can use it. As concerns the second property here, it says that globally, so for all states, if I have weighting of C3, so token C3 in place weighting, I will then eventually in the future have BZ of C3. So place BZ will contain token C3. So whenever a process C3 requests to enter the critical section and to hold the resource, it will eventually succeed. So at this stage, you've seen how to build a reachability graph, how it can be used for system analysis. You have seen how to express properties with LTL logics, and now we'll see about CTL logics to express additional properties in the next sequence.